in this question, we're going to find the expectation value of the Hamiltonian, which was already found out to be this glob of constants in the example problem, but we're going to have to do it, quote unquote, the old-fashioned way. So we're looking at this wave function right here that's frozen at time equals 0. It's the wave function is this, and it exists in an infinite square well from 0 to a. So going back to the Hamiltonian here, so the old-fashioned way is just simply doing a hard integral. Well, I mean, it's not hard, but not doing it the way that we did it before, which is basically just summing up all of the coefficients, all the probabilities, and then averaging all those values. So this is the full old-fashioned way of finding the Hamiltonian right here. All right, let's see if we can get it done then. Right, and the important thing to note is that the complex conjugate of the wave function right here is just simply nothing changes, right? Because there's no complex values in here, so it just is also equal to the wave function here. But one thing that we got to worry about for this problem is actually the operator form of the Hamiltonian, which is just h bar squared over 2m, right? With the curvature or the second derivative in respect to space. So actually, typically, it's usually like the full Hamiltonian is also has the potential here. But remember, inside an infinite square well, the potential here is actually equal to 0. So this whole term just goes to 0, and we're kind of just left with this portion right here. So we'll go ahead and plug that into our integral that we have. And we already found out what a was. I mean, we didn't do it, but the author did it in the textbook. We figured out he already solved for the normalization constant, but we're just going to leave it just to make it easier, and we'll just throw it in at the very end. So here we go. Oh, forgot an x. All right, so now we got all that, so we can just go ahead and, as you can see, the main thing here is just this derivative. So the first derivative, let's see here, just do it real quick, is a over 2x, right? So the second derivative would be just -2 here. All right, and we can also throw out these constants to the front. So let's go ahead and rearrange everything in a more organized fashion. So a squared, and again, we know what that is. We're just going to throw it in at the very end. 2m. I'll just go ahead and throw the -2 out in front here. Let's see here, from 0 to 8. And then we're just left with this now. Right, that's a relatively easy integral. Let's cancel out the 2's. The negative becomes a positive. We got a squared. Let's see here, h bar over m. And that integral is just a, let's see here, x to the, right here, x to the third. Right, evaluated from a to 0. Right, and then let's see, we got our glob constants, which I'll just slide down here. What is this? So we can just do common denominators here. That's a 2, right? Oops, no, this is a 3. Almost missed it. All right, so that is, let's see here, a third over 6th, right? And so now our a was found just in the example problem was 30 over a to the 5th square root. So that was in the textbook right there, so we didn't have to figure that out. So let's see here. So if that's a squared h bar squared over 2m a to the third over 6, and that will all equal, let's see here, substitute an a in, 5 h bar squared over ma. Yeah, and yeah, that's it. We got it. So it turns out doing it the old-fashioned way right here is just essentially the same way as doing it where we just do the, when you just like weigh all the energies by their respective probabilities and then summing them up for all the possible states that they could exist. So it ends up working out, so not a bad problem.